There you are. Great. Okay, so hopefully you can see that okay. Thanks for the introduction, Richard. Yeah, and thanks everyone for tuning in. I've enjoyed many of the other talks that you've hosted, and look forward to many more. It's been a bit of a highlight of lockdown for me. So yeah, I'll be talking about dietary sugars, exercise and metabolic health. And I'm specifically avoiding the role of sugars in dental health and focusing on metabolic health. There is a reasonable amount of evidence actually that dietary sugars have a negative effect on dental health, but I won't be going into that. It's not really my area. So I'll be focusing on metabolic health, and in that sense, glucose and lipid metabolism. So I'll just start with any potential conflicts of interest. So here are the funders of either the research that I've done or myself, just so you're aware. And in addition to funding as a potential conflict of interest, we should also probably highlight relevant personal biases. So mine is that I love milk and also exercise. And the reason I've specifically stated those two will become clearer as I go through the talk. But that isn't me in the photo. So if we look at the guidelines for sugar intake, either by the World Health Organization or the Scientific Advisory Committee on Nutrition in the UK, they all generally restrict the intakes of free sugars. So the specific quote here is that population average intakes of free sugars should not exceed 5% of total dietary energy for age groups from 2 years upwards. Now, I'm not a huge fan of prescriptive guidelines in the general sense, mainly because I'm not sure there is one particular optimal diet for health. It depends on many factors, including the physical activity context of the individual. But nevertheless, this is probably a reasonable guideline for the general public. And the basis of that guideline is because they specify free sugars rather than other sugars, because there is no reported evidence of adverse effects of consumption of intrinsic sugars and sugars naturally present in milk. Therefore, the recommendations of this guideline focus on the effects of free sugars. And free sugars can be defined as all monosaccharides and disaccharides that are added to foods by the manufacturer, cook or consumer, plus sugars naturally present in honey, syrups and unsweetened fruit juices. Under this definition, lactose, when naturally present in milk and milk products, is excluded. So the restriction of free sugar intake is specific to sugars that are added to products, whereas sugars that are naturally present within fruits and vegetables, for example, there's no limit on their intake in terms of this guideline, and equally there's no limit in terms of milk sugar intake. So it's just worth bearing that in mind as we work through. I'll now focus on some of the physiology behind this, and we can kind of test whether these guidelines are appropriate under all conditions. So just to start with the basics and some clearer definitions of what sugars are, I have to remind my mother, or at least I was surprised I had to remind her about a year ago, that sugars are indeed a subset of carbohydrates. And typically from a chemical basis, we would define sugars as either monosaccharides or as disaccharides, so one or two molecules. So glucose, fructose and galactose are the main monosaccharides in the diet. And then the major disaccharide is sucrose that most of us would consume. That is a glucose molecule and a fructose molecule bound together. There's also the disaccharide maltose. Lactose is also known as milk sugar. And then there's isomaltulose, which you can see looks very similar to sucrose. So it's also a glucose fructose disaccharide, but the bond that links those two is much more difficult to break down, and so it's a disaccharide that's more slowly digested and absorbed, so it produces a lower glycemic response. It also is less cardiogenic, so better for dental health. We've then got oligosaccharides, which are chains typically of glucose molecules between 8 and 12 in length. And the major one here is maltodextrin. And that's actually high glycemic index. So when you eat maltodextrin, you get a similar glycemic response to glucose. So its glycemic index is essentially 100. And herein lies a bit of complexity, because we might classify carbohydrates as simple and as complex. And complex means the chains of glucose molecules. But in fact, they can behave very much like the simple sugars. So you can take your Angel Delight, your sugar-free Angel Delight, and there won't be any glucose or sucrose in there, but there will be maltodextrin. And so the glycemic response to your sugar-free Angel Delight is probably very similar to the full sugar version. Polysaccharides would be chains of glucose molecules that are much longer, typically starch, and we can get two different types. There are many more, but the two main ones would be amylopectin, which is a high glycemic index starch. And you can see it's got this branch-like structure, whereas amylose is lower glycemic index, and that's typically in these long, thin chains. And the reason that the amylopectin is higher glycemic index is that this branch-like structure means that digestive enzymes can access the molecules much more readily. So it's got a bigger surface area for action, for digestion. Now, the major sugars that we would consume in our diet are mainly sucrose, so that's known as table sugar. And we might also have small amounts of free glucose and free fructose within things like honey and other syrups. But fructose is the main thing we think of when we think of dietary sugar. It's commonly thought of as an evil aspect of the diet. We commonly hear negative things about high fructose corn syrup, and so it's thought that fructose is the key aspect of sugar that has the negative health impact. So we'll be focusing on that mainly. So I mentioned at the start that I'll be discussing metabolic health, and by that I mean glucose control and lipid control or fat control. And just to briefly introduce the concepts of glucose and fat metabolism, here we've got glucose metabolism in the fasted state. And in that state, most of the glucose that's appearing into the circulation is coming from the liver, from the breakdown of glycogen and from gluconeogenesis. So that is released into the circulation and it's taken up by peripheral tissues. In the fasted resting state, that will be predominantly the brain, but if, of course, we're physically active, then more will be directed to muscle. In the fed state, we get an increase in the appearance of glucose from the small intestine now, and we get an insulin response as well. And that will have a number of effects. It will suppress glucose output from the liver, and it will also stimulate glucose uptake into muscle and into adipose tissue. If we compare that to fat metabolism, there's a few similarities and a few differences. So we've got very low density lipoprotein production. So that's secreted by the liver into the circulation. And that's partly formed from non-esterified fatty acids that are released from adipose tissue to the liver. These are then the lipid from these particles are taken up by peripheral tissues. And in order to do so, they need to be broken down by lipoprotein lipase. And insulin has opposite effects on adipose lipoprotein lipase and muscle lipoprotein lipase. So insulin stimulates LPL within adipose tissue, but it actually modestly inhibits LPL within muscle. And in adipose tissue, the major fate of lipid would be storage, whereas in muscle, the major fate would be oxidation. And this isn't a 100% efficient process. A small amount is remaining in the circulation, and that's known as the remnants. So then when we eat a meal containing fats, we have some chylomicron triglycerides coming from the small intestine. These are now compete for clearance with the VLDL. And because LPL's, the lipoprotein lipase has a greater affinity for the chylomicron tag, they're more likely to be broken down and taken up by adipose tissue, essentially resulting in a bit of a backlog for VLDL, and we get an increase in the concentration of triglycerides in the blood. And essentially for both glucose and triglycerides, we want to buffer this increase when we eat a meal and keep a relatively low concentration throughout the day. You can see the consequences of high triglyceride concentrations here on the right. Also, if you've seen the documentary Game Changers, you'll be familiar with this type of image. The plasma on the left there, you can see, is very clear, whereas the plasma on the right is extremely hypertriglyceridemic, looks very thick and turgid. And the reason it goes cloudy color is because the diameter of the chylomicrons just happens to be about the same as the wavelength of light, and so they scatter the light and make it cloudy. You can also see the action of lipoprotein lipase across adipose tissue if you sample from an artery that goes to adipose tissue and a vein that drains the adipose tissue. And you can see that it's slightly less cloudy, the blood on the right-hand side compared to the left-hand side, and that's because the adipose tissue has taken up some of that triglyceride. You might be thinking how they actually sample this, and we've got Keith Frayne to thank for developing that method. You can see on the left-hand side the anatomy of the veins that drain various tissues there, and the great saphenous vein is at the bottom. That's the one that you cannulate if you're looking to drain the subcutaneous abdominal adipose tissue. That technique was pioneered by Keith Frayne, and as a result, that vein also became known as the Great Vein of Frayne. Fortunately, I got to take part in a study in Birmingham in the last year where we employed this technique. So they're sampling my great saphenous vein. They're also sampling a radial artery on my left arm, and also a deep femoral, a deep vein on the right arm to get arteriovenous difference across muscle and adipose tissue. And using those methods, these kinds of data can be generated. So these were generated by Keith Frayne's lab in Oxford. And what they did is, in addition to those measures, they included tracers in meals, and they could see how much then of the glucose and the fat from the meal that's been ingested has been taken up by these two tissues. And they studied this response over a full day, so they could characterize breakfast, lunch, and dinner. So what you can see here in this figure is the percentage of the meal glucose in the black bars and the meal fat, which is in the open bars, from breakfast, lunch, and dinner. And this is the proportion that's taken up into muscle. So you can see that muscle clears approximately 50% of the glucose from a meal that you ingest, and around 40% of the fats from a meal that you ingest. If we look at adipose tissue on the right-hand side, then less of the glucose from the meal is taken up by adipose tissue, so less than 20%. But interestingly, the amount of fat that's taken up by adipose tissue increases across the day. So it goes from less than 20% with breakfast, and bear in mind these meals were matched for macronutrient content. This increases across the day such that by dinner time, about 50% of the meal fat is stored within adipose tissue. That's a healthy response. We want to be buffering the blood concentration. So it's a good thing that adipose tissue takes up that dietary fat. And what you see in severe obesity is that you get a down regulation of this response. So it's a bit like the adipose tissue is full. It can no longer store any more fat, and therefore we get a rise in triglyceride concentrations. So just to summarize the introduction, sugars are a subset of carbohydrates, and nutrition guidelines commonly recommend restricting the intakes of free sugars. Most concerns over sugars center on fructose-based sugars, and that's with respect to both karyogenicity, so oral health, but also metabolic health. And the things that most people are concerned about there are the effects on blood glucose and lipids. And the regulation of blood glucose and lipid concentrations involves a coordinated response of many different tissues, such as the liver, muscle, and adipose tissue. And each of these could be influenced by sugar consumption. So what does high fructose intakes do to our metabolism? Well, on this slide, I'll just go through some of the the broad data before delving into the physiology. And what I'm looking at here is the evidence from systematic reviews and meta-analyses, because there's actually quite a lot of evidence of what high fructose intakes do. And we should also consider here whether we're talking about substituting high fructose for other carbohydrates or even fats, or whether we're superimposing high fructose intake onto a baseline diet. So a common misconception is that high fructose intake impairs insulin sensitivity in general. It certainly does seem to impair insulin sensitivity in the liver, and that's either with isocaloric substitution, or if we're overfeeding people with excess fructose, we see a reduction in hepatic insulin sensitivity, or in other words, increased glucose output for a given insulin concentration. But the part that's a bit of a misconception is that most people think that high fructose intake impairs peripheral or muscle insulin sensitivity. And that doesn't seem to be the case, either with isocaloric feeding or hypercaloric feeding of fructose. Insulin sensitivity in muscle seems to be broadly unaffected. Another common aspect is that we see an increase in intrahepatic lipid content, and that seems to be mainly when it's a hypercaloric overfeed of fructose intake. So we see an increase in lipid content in the liver. We also see an increase in LDL cholesterol concentrations, and that's seen even with just isocaloric substitution. But we see a decrease in glycated hemoglobin. So it's not a case of fructose is bad in all aspects of physiology and health. It may be the case of fructose could be detrimental for some aspects, such as LDL cholesterol and hepatic insulin sensitivity, but it could actually be beneficial for some aspects, such as glycemic control in the postprandial state anyway. One thing that a lot of people are commonly surprised about is the idea that adding small amounts of fructose can actually improve glucose tolerance, and that's known as these catalytic doses. So this is one of the first studies to have shown this response in humans. It was from Alan Cherrington's group. And what they did is they gave people an oral glucose tolerance test. So that's 75 grams of pure glucose. And they either had that on its own, or they added an extra 7.5 grams of fructose to that 75 grams of glucose. And what you can see here is the black circles are when the fructose is added, and the glycemic response is lower compared to when fructose was not co-ingested with the glucose. And what they think is going on here is that in a normal condition, glucose taken up by the liver is converted into glucose 6-phosphate by glucokinase. And that's a rate limiting step in hepatic glucose metabolism. There's also something known as the glucokinase receptor protein. And in a normal state, when that's bound to fructose 6-phosphate, then it has a greater affinity for glucokinase. And so it's inhibiting glucokinase activity and slowing down essentially glucose uptake into the liver. When we co-ingest fructose, we get an increase in fructose 1-phosphate concentrations in the liver. As you can see, that's the first step of fructose metabolism. With high fructose 1-phosphate concentrations bound to GKRP, that alters GKRP affinity for glucokinase. Glucokinase is therefore more active, and we can get more glucose phosphorylated and increased glucose uptake into the liver. So in other words, co-ingesting fructose with glucose increases glucose uptake into the liver, and that might contribute to this glycemic response. If we actually measure liver glycogen content with fructose infusion, we see a potent effect at relatively small doses. So these are data in humans, and they measured net glycogen synthesis within the liver in response to an insulin infusion with and without fructose infusion as well. And as I say, they only infused a small amount of fructose. It was only 9 grams over a full 4-hour period, so not very much at all. And yet we see this massive increase, relative increase in liver glycogen synthesis. And in this study, they also managed to determine whether this increase was due to a change in glycogen synthesis rate or glycogenolysis rate. So just to put that in perspective, if you look at the diagrammatic on the right-hand side, showing the steps of glycogen synthesis and glycogenolysis, you should bear in mind that under all conditions, both of these processes are happening. So there's a constant turnover of glycogen, but it's just the relative rates of glycogen synthesis and glycogenolysis that determine the net effect on glycogen synthesis or breakdown. And using these methods, they showed that fructose specifically affects the glycogen synthesis rate. So glycogenolysis or glycogen breakdown is unaffected, but fructose stimulates glycogen synthesis to increase net glycogen synthesis over this period. Now, we should bear in mind that that intravenous fructose infusion may not be the same as ingesting fructose in humans or in other models, actually. And there's been a couple of studies by Josh Rabinowitz suggesting that the intestine plays a major role in fructose metabolism. And so if we're intravenously infusing the fructose, then tissues like the muscle and the liver might actually see higher concentrations of fructose than they would do normally. Because these data, in rodents at least, suggest that a lot of the fructose metabolism at low doses is done by the intestine, and therefore the liver doesn't actually see very much fructose. It mainly sees glucose and lactate, which is what fructose is converted into. So that's just a caveat to consider, but we do have some data in humans showing that at least large intakes of fructose also enhance liver glycogen synthesis in humans as well as in rodents. Most of these studies are done in a post-exercise state. This was the first study to clearly show it. They gave 150 grams of glucose over about a six and a half hour period. And that was ingested alongside glucose. And you can see that the fructose condition, which is in the triangles, potently stimulates net liver glycogen synthesis compared to glucose only, which is in the solid circles. Just an interesting point that we'll come back to later is that they also studied the effect of galactose or milk sugar on glycogen synthesis. And you can see it looks very similar to the response to fructose intake. This was followed up by Cass Fuchs, who gave an even higher dose of fructose, 280 grams of fructose over a 5-hour period, and showed the same response. So clearly, fructose can stimulate liver glycogen synthesis. In humans, this certainly happens with large doses. It would be interesting to see what happens with much smaller doses of fructose. And this might have implications for metabolic health. And the implications are because once we've saturated our capacity for glycogen synthesis, we need to do something with that carbohydrate. If we can't store it as glycogen, then one of the fates could be converting it into lipid via de novo lipogenesis and storing it that way, because it's safer to store that excess energy as fat than as glucose circulating in the blood. So just to put this in perspective, our glycogen stores are hugely limited compared to our fat stores. So the black bars here are the lower limit of each of these energy stores, and we can see on the left liver glycogen, in the middle muscle glycogen, and on the right adipose triglyceride. And the lower limits here were taken mainly from starvation studies such as the Minnesota starvation experiment. And you can see that liver and muscle glycogen concentrations can get very, very low. On the opposite extreme, if you take a well-trained athlete who's been consuming a high carbohydrate diet, they're going to have the highest glycogen concentrations of all. And you can see that the top of those white bars, that's the highest amount of glycogen that has at least been reported. So if you add up liver and muscle glycogen there, it comes to just over 3,000 calories worth of energy that humans can store as glycogen. Compare that to our fat stores. And even if we look at the lower limit, we're going to have to change the axis here. The lower limit that seems to be compatible with life in humans is at least 23,500 kilocalories of energy. And then the upper limit of adipose triglyceride storage is potentially infinite, but at least it's been reported in severely obese people to have been about 731,000 kilocalories of energy. So clearly the capacity to store glycogen is limited, and once that's saturated, we're going to have to do something with that, and we could be starting to produce fat from non-fat sources, as illustrated by those arrows. And that might be one way in which fructose and glycogen are involved in lipid metabolism. So if we look at some of the early studies that gave people fructose and looked at triglyceride concentrations in the postprandial state, this is again from Keith Frayn's lab, we can see that an acute bolus, so this was quite a large bolus of fructose, it was about 50 grams, compared to glucose, co-ingested with essentially a high-fat milkshake, you get an exaggerated triglyceride response. There's higher triglyceride response to fructose ingestion compared to glucose ingestion. And the mechanisms that might underlie that could be multiple. So one of them might be de novo lipogenesis. So that is the conversion of carbohydrates into fat, or precursors, if you like, into fat. And in that study, they did measure the conversion of fructose into lipids. So they used carbon-13 labeled fructose and traced its conversion into palmitate and other lipids. And whilst that did happen, and fructose was more likely to be converted into fat than glucose, it happened at a very low quantitative rate. So it couldn't actually explain this triglyceride response. But that method misses out on other things that could be going on. So nowadays, to measure de novo lipogenesis, a lot of people use deuterium oxide. And whereas with a carbon labeling method, you're only tracing one precursor into however many products that you measure, normally one precursor to one product, or in other words, the fructose conversion into, say, palmitate. Using deuterium oxide, you're essentially measuring the whole de novo lipogenic process. So all of the precursors to all of the products. And it could be that fructose stimulates the process of de novo lipogenesis. So by having fructose present, you're not just converting the fructose into lipid, you're also converting more glucose into lipid and more lactate and other precursors. So that's just one thing to bear in mind. The other is that this could be due to a decrease in fat oxidation. So even though fructose produces a lower insulin response, it seems to quite potently suppress fat oxidation. And if we've got lower rates of fat oxidation in muscle, we're going to take up less triglyceride from the circulation, and that could also cause this increase. Or it could be due to differences in VLDL secretion from the liver. So insulin suppresses VLDL secretion from the liver, and because fructose produces a lower insulin response, there might be less of a suppression of VLDL secretion. And just to kind of illustrate that point as a reminder here, insulin suppresses VLDL production, so that could explain that response. Now, what's interesting is that this response of fructose on de novo lipogenesis, at least when measured with deuterium oxide, seems to be a linear relationship. So these are studies that are already published, and I've just started pooling them together in terms of the acute fructose intake on the x-axis, and then on the y-axis, the fractional hepatic de novo lipogenesis rate, and it's expressed as, that's always expressed as a percent, so the percent of lipid that is de novo, and that's also expressed above the fasting concentration. You can see there seems to be a bit of an outlier there, the Steenson study, and that's a relatively recent study published in Nutrients if you want to have a look. It was ambitious of them to measure or to attempt to measure intestinal de novo lipogenesis alongside hepatic de novo lipogenesis. Have a look at the methods. It's above me as to whether they've achieved that or not, but at least given that most studies show a substantial and robust increase in de novo lipogenesis with that dose of fructose ingestion, they show a relatively modest response. Maybe there's not, they haven't quite achieved that, the validity of that method, but they should probably have some recognition for at least giving it a go. One thing we were interested in was to see how galactose influences postprandial triglycerides. So fructose has received a lot of attention. You know much less about galactose. And John Watkins did this as his master's project, and he's now a PhD student with us. He studied the response of triglycerides to galactose ingestion with a high-fat drink and compared that to glucose. And we collaborated with Kevin Dayton at Leeds Beckett to compare with fructose as well. So what you can see on the left-hand side is the glucose-galactose comparison and the postprandial triglyceride area under the curve. And you can see quite a distinct increase in the triglyceride response when galactose is ingested with a drink compared to glucose. And on the right-hand side, you can see the fructose compared to galactose treatment. And there doesn't seem to be any clear difference between those two. So it seems based on these data that the triglyceride response to galactose ingestion is more similar to fructose than it is to glucose. And if we have a look at other aspects of the hormone and metabolic profile, then galactose also seems to be more similar to fructose in those ways as well. So on the left-hand side, again, we've got the glucose-galactose comparison. On the right-hand side, we've got the fructose-galactose comparison. These are the insulin responses that I'm showing you now. These are the non-esterified fatty acid responses, so actually similar between all the conditions. But the most interesting one of all, to me at least, was the lactate response. So you can see that galactose stimulates a postprandial rise in lactate concentrations, and that seems to be similar to the increase seen with fructose intake as well. Now, the reason that this is interesting is because of what we think we know about the metabolic fate of galactose. So if we look at the processes as we may see in a typical textbook, on the left-hand side, we've got glucose and fructose metabolic fate in the liver. And on the right-hand side, we've got the galactose metabolic fate. And in a textbook, it will say that the major pathway of galactose metabolism is the Lenoir pathway, which ultimately results in the conversion of galactose to galactose 1-phosphate and ultimately UDP, galactose and UDP glucose. And so to a large extent, the galactose is converted to glucose and should be behaving like glucose. Now, it's also thought that with de novo lipogenesis, with fructose intake, that a major pathway for de novo lipogenesis is via lactate production. So on the left-hand side, you can see the conversion of pyruvate to lactate and ultimately triglycerides, that lactate could be a major precursor there. So given that we've seen this increase in lactate with galactose, and also given the previous data regarding galactose and glycogen synthesis, it would be interesting to see if galactose has the potential to stimulate de novo lipogenesis. And luckily, we've got some funding from British Heart Foundation to try and explore that a little bit further. So to summarize that section, fructose increases hepatic glucose output and plasma LDL cholesterol concentrations, even when just isocalorically exchanged for other carbohydrates. So those are some of the negative metabolic health effects of high fructose intake. But it does lower postprandial glycemia, so it's not all bad. Fructose potently stimulates hepatic glycogen synthesis, which could contribute to glycemic control. And fructose ingestion can increase postprandial triglyceride concentrations. Galactose seems to produce a metabolic milieu that's more similar to fructose than to glucose, and this raises some interesting questions about what we know about galactose metabolism. So all of this is within the context of studying relatively sedentary individuals. And one thing that's commonly not considered in public health guidelines is the physical activity status of individuals. And that might have a really potent effect on the metabolic consequences of high sugar intakes. And we can learn a lot from these guys here, the people at the elite end of the spectrum for endurance exercise, because they consume a hell of a lot of carbohydrate, and a lot of that is sugar. So when we study cyclists, we see that they're exquisitely insulin sensitive compared to people who aren't cyclists. And also they have very low triglyceride concentrations. In almost all aspects of metabolic health, we class them as healthy. However, if we look at their energy intake and the types of foods that contribute to their energy intake, all of the red in this pie chart is essentially sugar. So you can see sweet cakes, a maltodextrin drink, sugar, table sugar, skimmed milks, soft drinks, and isotonic sports drink. The yellow is other carbohydrates, and then the blue is kind of your animal products. And in a Grand Tour scenario, these riders would probably be eating about 500 grams of sugar per day and a kilo of carbohydrate, and yet they maintain this exquisite metabolic health. So that's interesting. It is obviously an extreme example. So we can look at a bit more of a relevant example to you and I. And these are some data from Luke Tappy's lab. What they did is they got people into the lab on 3 occasions and studied them with these 3 treatments. So one of them is in accordance with typical guidelines. So less than 5% of their energy intake was from sugars. Then they had a high fructose condition. So 30% of their energy intake was from fructose. So a very high fructose intake. And then the third condition was still 30% of energy intake from fructose, but they exercised on every day leading into the test period. And what they did is to account for the excess energy that had been expended through exercise, they replaced that energy with even more fructose intake. So that third group were having the highest fructose intake of all in an absolute sense, about 208 grams per day. And that's equivalent to 41 teaspoons if you prefer Daily Mail units. The exercise wasn't extreme, so it was about 2 times 30 minutes at 125 watts. So it's not kind of elite cyclist levels. It's relatively achievable for most people. And in terms of the fasting triglyceride concentration, what they saw was in just 4 days of high fructose feeding in sedentary individuals, we see this quite marked increase in fasting triglyceride concentrations. But if we exercise on each of those days leading into this, as we're consuming the high fructose intake, even if we replace the excess energy expended through even more fructose intake, it obliterates this triglyceride response. So exercise prevents fructose-induced hypertriglyceridemia, and this effect is independent of the effect on energy balance. So what's going on there? It seems that exercise is a pretty potent way to maintain metabolic health, even if there's a high fructose intake. And Aaron Hengist, who I think is watching at the moment, wrote this review along with Francoise and myself. And have a read of it if you're interested more. We kind of speculate that high liver glycogen content explains, or at least is a contributing mechanism to how fructose increases de novo lipogenesis, and also might explain why exercise can reduce triglyceride concentrations on a high fructose diet. So the idea is that fructose stimulates glycogen synthesis, as I've already shown you. And as we have a high glycogen content in the liver, the processes involved in net lipid synthesis are all upregulated. Whereas if we've got a low hepatic glycogen content, either by reducing sugar intake or through exercise, then all of the processes involved in net lipid synthesis are downregulated, and we get lower triglyceride export from the liver. Some of the aspects or some of the data that might kind of support this idea are that in rodents, if you knock down hepatic glycogen synthase, so you don't allow the liver the ability to store carbohydrate as glycogen, then you get an increase in de novo lipogenesis. And also if you increase hepatic glucokinase, so essentially you're increasing the throughput of glucose into the liver, then that also increases triglyceride concentrations. But you don't see an increase in triglyceride concentrations if you increase the capacity for glycogen storage. So if you increase protein targeted to glycogen, that increases the capacity for glycogen storage in the liver, and that doesn't influence triglyceride concentrations. So just to expand into a slightly broader area in terms of other sugars and carbohydrates more generally, and mainly because I just saw Harry Taylor on as well. This was a study that he conducted to understand the effects of exercise with and without replacement of that carbohydrate on health in terms of oral glucose tolerance. So what he did as his master's project was got people to, on day one, to run for 90 minutes at 70% of VO2 max. So they've become glycogen depleted in both liver and in muscle. Then immediately after exercise, they started to either replace those carbohydrates with maltodextrin. And what was quite neat about this study was that Harry measured carbohydrate oxidation during exercise using indirect calorimetry. So that replacement was done to try and match the carbohydrate that had been burned. So we'd restored their carbohydrate balance. Or they retained the carbohydrate deficit. So they didn't consume any maltodextrin, they consumed a placebo. On both occasions, they then had a relatively low carbohydrate meal in the evening, essentially a chicken salad. They then went to bed and slept overnight before coming in for an oral glucose tolerance test the following morning. And what he found was that when you replace the carbohydrates that have been oxidized during exercise, then the following morning, oral glucose tolerance is impaired compared to if you retain that carbohydrate deficit. So on the left, you can see the glucose concentrations are elevated when the carbohydrates have been replaced. On the right-hand side, you can see the insulin concentrations are also elevated. This was a surprise to me, actually. I did expect to see a change in insulin concentrations, but it's actually rare to see a change in glucose concentrations in healthy individuals. You normally see the compensatory change in insulin. This has been followed up by Drew, who's just finished his master's and is looking to start a PhD soon, to extend this a little bit further and see how this actually compares to a resting condition, because we don't know if those two exercise conditions still showed an improvement in glycemic control compared to rest, or whether the replacement actually impaired glycemic control compared to rest. So he very similarly replicated that study, but had an extra condition here, which is the resting control condition. And these data are the Matsuda insulin sensitivity index. So if you like, combining those glucose and insulin data to get a composite measure. And the higher this number, we'd say the better insulin sensitivity, or if you like, better metabolic health. So you can see that exercise when the carbohydrate deficit is retained produces an increase in insulin sensitivity measured the following morning with an OGTT. Whereas if you replace the carbohydrates after exercise, that seems to abolish that benefit of exercise on the insulin sensitivity index. So at least some of the effects of exercise on glucose control do seem to be due to glycogen use, or at least carbohydrate balance. So again, another way in which sugars might influence metabolic health, and this quite interesting and complex interaction with exercise. So to finish off, fructose stimulates hepatic glycogen synthesis, which may partly explain the higher net lipid synthesis following high fructose intakes. Ingesting sugars when glycogen stores are already close to saturation may further increase net lipid synthesis. The glycogen depletion or turnover of exercise is likely to play a role in mediating the metabolic health benefits of exercise. And the effects of milk sugars, such as galactose, low dose exercise, and also the effects of biological sex would all benefit from further research, because we don't know very much about each of those areas. So that just leaves me to thank everyone who does the work in the lab, and also our collaborators around the UK and abroad, and thank you for your attention. I think you're on mute, Richard.
And there was, can you hear me now?
Yeah.
That was probably the best question I've ever asked, and now I can't remember what it was. So you'll never know what that was, but it was great talk. Thank you. And thanks for going into the basics of sugar right at the beginning, because I think that's really important to understand the sort of slight differences before you go into trying to understand the really complex bits of metabolism, which you went into and you explained really well. I've got a few questions myself, but I'll open it up to the floor. We've got Joseph wants to know, says, hi, thank you for a great talk. Is there any reason you prefer the Matsuda index as opposed to other estimations of insulin sensitivity, essentially?
Yeah, not particularly. So there is a good paper actually that's compared different equation-based measures to essentially the M value from a hyperinsulinemic euglycemic clamp, and showing the correlations of all the different ones. The Matsuda is up there. It wasn't the one that had the highest R, but there's not much between that and some of the other measures, such as there's one known as the oral glucose insulin sensitivity index. Matsuda seems to be the most common one that I see in the literature. So at least for a comparison to other studies, there's a rationale there. And certainly I do prefer the postprandial indexes rather than the fasting. So the HOMA IR is useful obviously for population studies where we can only really get a single blood sample. But if you've got postprandial measures, then they seem to be able to be more sensitive to detect small changes. And they're also more reflective of peripheral insulin sensitivity, whereas the HOMA IR seems to be more influenced by hepatic insulin sensitivity than peripheral.
Hopefully that answers your question, Joseph, unless you've got anything you want to add to that. I got a quick question just whilst maybe some others are coming through. With the study which you got individuals to exercise at 70% of VO2 max and used indirect calorimetry, a really useful way of then determining how much sugar they need to replace lost energy with. I was wondering, at 70% of VO2 max for 90 minutes, that's going to be, how fit were these guys?
Yeah, they were. It was one of those proof of principle studies, and we chose that intensity because it's carbohydrate dominant. So we wanted to essentially get them to oxidize as much carbohydrate as quickly as possible. And yeah, most people running that intensity, they have an RER close to 1, and it's almost 100% carbohydrate oxidation. That was the rationale. Of course, yeah, it has slightly less relevance and to other scenarios. Some of our overfeeding studies as well use a very similar intensity. There's some work that should be coming out soon from Dr. Jean-Philippe Wallan from Bath, where he's looked at different types and intensities of exercise and the potential health effects during overfeeding of those different modes and intensities of exercise. From memory, it seems like intensity does matter, but I won't steal his thunder too much.
Great, thank you. Yeah, I was just wondering what the kind of RER values would be a bit like from that study. I would have volunteered in my younger days, maybe not now. A quick question about hepatic insulin resistance with the ingestion of fructose. Now, I know you didn't go into that per se, unless it's when I was running outside to rescue my dog. I was wondering if anyone's measured that, because obviously you're kind of, and it's certainly not a criticism, but you're making assumptions, aren't you, when you're talking about insulin resistance or hepatic insulin sensitivity. I was wondering if anyone's been able to measure that directly, whether in rodents or humans, in response to high fructose, because you've done a great job of trying to piece it together, and I certainly learned a lot tonight. And just, it's just the more you delve into, the more confusing it gets. So anyway, the question is, have they actually looked at that?
Yeah, I mean, it's a great question. And I was probably, to use the term hepatic insulin sensitivity is a bit of a broad stroke. I should have been more precise really and said hepatic glucose production, because with the muscle, in a way, it's a little bit more simple. With the liver, if you really want to study hepatic insulin sensitivity, there's numerous angles to that in terms of the ability to suppress glucose production. So the ability of insulin, I should say, to suppress glucose production is one aspect, but also the ability to store glycogen is another aspect of hepatic insulin sensitivity, and that process seems to only be saturated when you have hyperglycemic, hyperinsulinemic clamps. And actually, to my knowledge, those haven't been done in response to a high fructose diet. So yeah, I guess what we can say is that high fructose intakes seem to reduce the ability of insulin to suppress glucose production by the liver. We don't know if they influence the ability of insulin to alter hepatic glycogen storage. And even that first point, and I've heard Luke Tappy talk about this before, and he's very cautious as to say whether that's a detrimental or just a neutral effect. So it might just be a normal physiological response to fructose intake is the conversion to other substrates. And so even the modest increase in triglycerides, you can argue whether that's physiological or pathophysiological, and similar with the hepatic glucose production probably. So yeah, I'll sit on the fence on that one, I think.
Yeah, I mean, and then you've highlighted the importance of energy, energy storage as well in that. So we're, as you were suggesting, pathophysiological, physiological, it's probably just, physiological until you get to a state of maybe obesity, and then it becomes pathophysiological. I don't know. But, yeah, thank you. So I just wondered, because obviously you mentioned that fructose, as you rightly just said, inhibits hepatic glucose production. And then that threw up the question. You didn't, I don't believe you did get your terms mixed up in terms of hepatic glucose production and hepatic insulin sensitivity. So I wasn't sort of catching you up on that. No one's coming in with more questions, so it's just me and you talking now, which is great. That's the way I like it. The outlier you saw with Stevenson's paper, at the 300-minute, the outlier of that paper.
Yeah.
Any ideas of what might be, because that's a big difference, isn't it? I mean, that could just be methodological, I guess, or do you think there's something more to it?
Yeah, I think it's probably methodological. So as I say, most of the other studies had just attempted to measure hepatic de novo lipogenesis, whereas the Steenson paper was attempting to measure intestinal de novo lipogenesis and hepatic, and maybe through doing that, they've potentially underestimated, or they might have it accurately described, and the others could all be wrong, I guess. I don't know, but it's interesting in that it is an outlier and should be followed up, really.
We've got a question come through from Eric, but I'll quickly, then I can stop. The de novo lipogenesis is sort of, you're measuring it 300 minutes, and that was sort of had my questions up earlier. I mean, do we know how quickly that process occurs in response to fructose? Because obviously we're measuring, you and others, not me, are measuring the products of de novo lipogenesis, and we're assuming that it's coming because of that fructose, that acute fructose ingestion, obviously not a chronic. So I was wondering if we know how quickly that process is upregulated.
Yeah, great question. I don't know if you know it with a lot of resolution. It certainly seems to rise within an hour of ingesting a high fructose bolus. And again, actually, a lot of these studies are using relatively high intakes and may not be relevant to typical intakes across a day. So yeah, it would be interesting to study also across multiple meals. So we get, as I showed at the start, actually, at least the adipose triglyceride uptake response seems to build across the day. It'd be interesting to study the de novo lipogenesis response across the day. Some have attempted it, not with the deuterium oxide method, I don't think, but I'll stand corrected if they have.
Yeah, that's pretty interesting. Thank you. So I'll stop now. So Eric, I don't know if you can read his question, but I'll read it out for the audience. So given the same glycogen levels following exercise versus following fasting, would you expect the same glucose and insulin response? What factors may separate these two physiological states apart from glycogen depletion?
Yeah, great question. And there have been a few studies that have looked at that. And what you tend to see with prolonged fasting is actually an impairment in insulin sensitivity rather than an increase. So with short-term fasting, you can see an improvement, but yeah, with long-term fasting and already healthy people, it actually impairs insulin sensitivity. A lot of that work's been done by Ian McDonald and also by someone called Stephen Stannard. And what they think is going on there is that under both conditions, you get high fatty acid availability. And with exercise, you oxidize those fatty acids, whereas with fasting, you're not necessarily oxidizing all of them. Some of them might be becoming more stagnant lipid moieties within muscle, and that could contribute to a reduction in insulin sensitivity. So you tend to see there higher glucose and insulin responses compared to the same glycogen depletion through exercise.
Great, thank you. Well, I think that's it for questions. One coming through. Here we are. So for Julian, thank you for a really interesting talk. How important is the role the micro for carbohydrate metabolism? Could two cyclists with different micro have different responses to carb intake? Could performance be improved with pre or probiotics? Lots of questions in there.
Yeah, there's a lot in that.
There is. Start with the first one, I guess, for micro metabolism.
So yeah, the gut microbiome is probably important for carbohydrate metabolism. It's tricky in terms of not only would the microbiome influence how we deal with dietary carbohydrates, but also the dietary carbohydrates that we eat also influence the gut microbiome profile. So it's a two-way interaction, and we really don't know enough about that. And so if you were to take, two cyclists with different microbiomes, would they have a different response to carbohydrate intake? They could do. But then if they've both been consuming the same types of carbohydrates for a prolonged period, then you'd probably see some adaptation in their gut microbiome to become more similar in their responses. This is speculation because we really haven't studied this enough. But ultimately, in terms of the final point of the question, in terms of could performance be improved with pre or probiotics, it could do in a variety of ways. Probably the most likely is just that having a healthy gut through pre or probiotic supplementation seems to reduce the risk of gastrointestinal infection, particularly when traveling and exposing yourself to high risk scenarios. And of course, if you've got a gut infection, you might either take yourself out of a race or at least reduce your ability to train on a number of days. So they could indirectly affect performance. There's also some evidence that they might influence exogenous carbohydrate oxidation rates as well. So Jamie Pugh's done some work on that as well. So I'll take a look at that if you're interested.
Great, really good response. Thank you, Javier. So no more questions. I think that's bringing the session to a close, and only 2 minutes out of time. So thank you for that. Again, thank you for your time. Glad we finally got around to arranging this after a few mishaps. Great to see you again. Thank you for all the questions, guys, and have a good evening.
Thanks, Richard.
Thanks. So I think just the two of us. Let me stop the recording so we can swear. How was